Consider the sequence. Consider the sequence. Consider the sequence 2, 4, 6, 8, 10. There is a finite sequence, and from here we can get the series 2 plus 4 plus 6 plus 8 plus 10. So again, this is a finite series that we have derived it from the finite sequence 2, 4, 6, 8, 10. Now, if this series is infinite, if you have 2 plus 4 plus 6 plus 8 plus 10 plus like that, we have an infinite series. And note that this series proceeds with the common difference of 2, which we shall call d as 2. So if we look for the sum of this series, and let's say in general the summation of xi, and I is from 1 up to infinity, x1, x2, x3, like that up to infinity, you will find that this is an expanding or an increasing series. It will go up to infinity. It will be such a large number. Therefore, we can say the sum of the infinite terms in this series is infinite. Now, this is a series that proceeds with a common difference of 2, and therefore we can say that this is an example of an arithmetic series or an arithmetic progression. We can have another one, for example, 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus up to infinity. You can see that this is a series with a common ratio of 2. A common ratio of 2. Again, just like the previous one, this one is again enlarging or increasing, becoming bigger and bigger. And therefore, if we look again to the sum of the infinite numbers of the terms in this series, it will also give you infinity. It will be such a very big number. Sometimes we have a series, for example, 1 plus a half plus a quarter plus an eighth plus up to infinity. You will find that the common ratio is a half. The common ratio is a half. So what is the sum to infinity of this particular series? This is a geometric series, just like the previous one. Geometric series, a series that progresses with a common ratio. But the second one here with the common ratio r is a half. This is a series that is converging to a certain fixed number. It is becoming smaller and smaller. But keen observation is that it won't be 0. So to get the sum to infinity of this particular series, we use the formula sum to infinity is the same as a, the first term, over 1 minus r. Our first term here is 1, and our common ratio is a half. And this one will give you 1 over a half, which is 2. In other words, the sum to infinity of this series equals to 2. So note that formula, sum to infinity or sum of the infinite terms in a series that has a common ratio of actually less than 1. The absolute value of r is less than 1, and it goes to infinity, then we use that formula. Now, note this. If you have 0.17171717, this is what we call a recurring decimal or a repeating decimal. A recurring or a repeating decimal. And this decimal can also be written as 0.17 plus 0.007 plus 0.00017 plus 0.0000017, and so on and so forth. You can write it that way. Yeah? You can write it that way. Note 0.17 plus 0.00017 plus 0.00017 plus 0.0000017, and so forth and so on. You will get 0.17171717. So this repeating decimal is now a series. It's a series. And you can see that this series is a geometric series with the first term as a is 0.17. The common ratio r is 0.01. If you multiply the first term with 0.01, you get 0.0017. If you multiply the second one with 0.01, you get that. And therefore, the sum to infinity of this series is the same as 1. A is over 1 minus r, which is 0.17 over 1 minus 0.01. And this will give you 0.17 over 0.99. 0.99. And you'll notice that this is the same as 17 over 99. You should leave your answer like that. In other words, it means that the series 0.17171717 converges to the fixed number, the fixed rational number 17 over 99. Note that another way to find the sum to infinity of this series is what we did back in high school, that we let R be 0.171717, multiply R by 100, we get R 100R 17.171717, and then you subtract the first from the second equation. So 100R minus R is 99R, 17 minus 0 is 17, and therefore the rational number is 17 over 99. So this number 0.171717 converges to 17 over 99. Make sure you leave the answer as the fraction.